Thank you, Raymond. Yes, I would have picked the same list. Thank you, everyone, for coming. Yeah, I want to talk about how mathematicians think about patterns. Well, I want to talk about how I think about patterns, and how quite a lot of mathematicians think about patterns. This isn't the only way to do it, but I want to bring out two features of patterns which are particularly important, which is the role of symmetry and the role of what's called symmetry breaking, which is clearly related, and I want to show you how patterns can be recognised, classified, but also understood to some extent in terms of those two basic mathematical ideas. And I'm going to go through four basic types of pattern: snowflakes, animal markings. Now, I gather there was an earlier talk in this little series about zebra stripes. I don't know exactly what was done in that, but there will be a little bit of overlap, and I hope I won't contradict what was said. I hope it will be a complementary view. There are many ways to think about these things, and in the Christmas lectures, we actually brought one of these animals into the lecture. You can find it on the Royal Institution website. You can actually download and watch the lectures. And I think it was lecture number 5. So we brought a 6-month-old tigress into the lecture room. So people on the front row, you should imagine a tigress being brought in on the end of a chain with 2 burly young men. Very well behaved tigress. But it was... Basically, I felt that was the pinnacle of my lecturing career. I've never been able to match that. I want to talk about sand dunes, and I want to talk about animal movement. Okay? So, let's start with snowflakes. So, here's a couple of modern pictures and one rather older picture of the remarkable structure of some, not all, but a lot of snowflakes. And the detailed structure is very, very different, but you can see that there is a remarkable 6-fold symmetry in the snowflake. I was watching a television program the other day, and there was somebody with an experiment said they don't do that. Well, they didn't do that in his experiment, but I think that's because it was so carefully controlled that actually, I think you need a little bit of random noise to smooth things out a bit to get this kind of symmetry. I'm not quite sure why his experiments didn't work, but a lot of other people's experiments do work. So there's still some mysteries about snowflakes, in fact. And I just want to emphasise that the 6-fold symmetry in this perfect form is not the only thing that can happen. Here is another form of ice crystal. And you can sort of vaguely believe this is some fancy relative of the 6-fold symmetric snowflake, but it's clearly not as regular. There are some very interesting questions you could ask about this picture. But let's just go to this. This is a real snowflake, chosen, I'm sure, to be pretty close to perfect. If you look, you can just see little bits where it's slightly melted. You can see if you look closely that this is not faked up, this is genuine. And what puzzles everyone is this mixture of the symmetries of the thing, and I'm going to explain those now, but also the remarkable variety within this range of symmetric structures. So the way mathematicians think about symmetry, since about 1830, is in terms of transformations, in terms of ways of moving an object, so that when you've moved it, if somebody looked away while you were doing it and looked back again, they wouldn't realise you'd done anything. So if I take this snowflake and I rotate it through 60 degrees, you really wouldn't see any difference. It would look exactly the same shape in exactly the same place. And if I rotate it through 120 degrees, 180 degrees, multiples of 60 degrees, the same thing works. In addition to these rotational symmetries, the snowflake has 6 reflectional symmetries. If I put a mirror in the right place and flip it over, it looks exactly the same. And so there's 3 red lines showing 3 mirrors, which in this picture go between the big lumps of the snowflake. And then there are 3 more green lines which run down the centre of the protrusions of the snowflake, and that gives us 6 more. So this snowflake has 6 symmetries that are rotations, another 6 that are reflections, 12 in all, and what really matters mathematically is not just how many, but the way these different symmetries relate to each other. What happens when you do several of them in turn? What do you get? And of course, one of the features that is automatic from this idea of symmetry as a transformation that leaves things unchanged is if you do 2 of them in a row, you leave it unchanged, and then you leave it unchanged again. So what does it look like? It looks exactly the same as it did to begin with. You've moved it twice, but that must be equivalent to moving it once, because the 12 I've shown you are the only ways to move a snowflake around by rigid motions and make it fit in the same position. So mathematically you can take 2 of these transformations and combine them together to get another one. So it's like a little multiplication table, if you wish. This transformation followed by this other transformation makes this 3rd transformation. This is called a group, and group theory is now a major part of mathematics and how we analyse symmetries. But I don't want to teach you any group theory, I just want to alert you to its existence. And just to make this point that this snowflake really is very symmetric. The top left-hand picture is that picture of the snowflake, just shrunk down. The next 5 to the right, I've rotated it through 60, 120, 180, 240 and 300 degrees. I actually did this on the computer, I just took the picture and twisted it. I did it clockwise, which is the opposite of the mathematician's usual convention, but no matter. And then the pictures on the bottom are the same thing, but I reflected it first. So we have 12, these are the 12 images of that snowflake under its 12 symmetries. And you have to look very hard indeed at these pictures to see any difference. Whereas if I did it 30 degrees, you say that's pointing in the wrong direction. Okay? So the puzzles are, where does this symmetry come from? What's the physical basis for this? And then after that, the other puzzle, okay, that's this particular snowflake, but there's all these other fancy looking snowflakes, lots of different structures, but they have this same group of symmetries. Way back, good many 100 years ago, Johannes Kepler was thinking about this stuff, and he wrote a little book called On the Six-Cornered Snowflake. De Nive Sexangula, I think it is in Latin. It was a Christmas present to his sponsor, who was paying his salary, basically. And in it he just did thought experiments about this puzzle of the snowflake and its 6-fold symmetry. And he worked his way through, and he thought about packing balls together, and you know, if you put a lot of coins on the table and push them together, you get a honeycomb pattern. And he kind of worked his way towards what we would now recognise as the idea that ice is a snow crystal, snow is an ice crystal, get it the right way around, and it is something in the atomic structure of the ice crystal that is governing this 6-fold symmetry. And this was back in the time when atoms were something the ancient Greeks had thought about and mostly dismissed again, and it was all kind of forgotten, and it wasn't until about 1900 that physicists actually started to believe in atoms. It's remarkable how recently that happened. So Kepler worked his way towards the beginnings of the way we would now tell the story, which is snowflakes are formed from ice, ice is a crystal formed from water. This is a picture of the particular form of the ice crystal that is occurring in normal ice at normal temperatures and pressures. And you can see the two different kinds of atoms, the hydrogen and the oxygen. Hydrogens are black, oxygens are white. And there is a sort of honeycomb structure to this. It's in 3 dimensions, it's not completely flat, but it's within this structure of the ice crystal as it grows that there is, among other things, there is this group of 12 symmetries, the hexagonal symmetry. Now, when you actually ask under what conditions do different forms of snowflake occur, this is experimental work, and the 2 important variables are the temperature, which is in degrees centigrade on the bottom, and the supersaturation, the amount of moisture up in the cloud where the snowflake forms, which goes up the left-hand side. And depending on the combination of those 2 variables, we get lots of different shapes. And at the top in the middle, under plates, you see these very flowery plant-like things called dendrites. You see sectored plates, which are like hexagons with more hexagons stuck on, which is what we were looking at just now. Below that, you see just thin hexagonal plates. And further down, it grows a lot more in the 3rd dimension. And you can look at this picture and see all of these different kinds of shapes, and some fancy ones that are not particularly hexagonal at all. And if you start playing with other variables, you can get more structure. But the source of the variety of a crystal grown at a uniform temperature and a uniform pressure, you can sort of predict roughly what kind of shape it will be. Why then do we see such variety? Well, let's just take a closer look at dendrites growing. So here is a little piece of a snowflake growing this tree-like structure. And in fact, what you see is that as the side branches get bigger, they put out their own side branches, very like a tree. As a tree puts out branches, the branches put out smaller branches, you get down to twigs. The snowflake does this as well. And it does it because of what physicists call an instability. If you have a flat edge to the crystal, but there's a little bump on it, which is going to happen just because a few bits of ice are going to stick to it. Under those conditions of temperature and supersaturation that cause this, that bump grows faster than the flat bits. So once you've got this little bump, it gets bigger. So this instability of the flat edge amplifies. So the conditions of temperature and pressure where the snowflake is affect the immediate pattern with which extra bits of ice get added on. Yeah? Well, now imagine a little snowflake going around in a big storm cloud. Now, it's a tiny little snowflake, ice is forming on it. At any given moment, at all of the points in this honeycomb 6-fold symmetric pattern, at all of those points, the conditions are pretty much the same at a given instant. So you go to your little diagram of what shape crystal you should get, and it does whatever it should do at that instant. So it does the same thing at each of the 6 corners. But a split second later, it's whirled around in the cloud, and the conditions are different. So now you kind of reset and say, oh, what do I do now? Oh, I grow this structure at all 6 corners. So because the snowflake is small, so on a very small scale, the conditions at the corners are pretty much the same. But on a larger time scale, the conditions at those 6 corners keep changing. You could actually kind of draw a picture of how the snowflake's temperature and supersaturation move around that diagram. And the rules for growing keep changing as it moves. Now there's an awful lot of ways to draw wiggly curves through that diagram. So there's a lot of different detailed shapes for your snowflake, but the 6-fold symmetry is actually preserved at all stages. And so the thing grows into this perfectly symmetric shape. barring accidents, this is all, this is not absolutely literally perfect all the time, but when you get one of these symmetric snowflakes, that's pretty much what's happened. So the symmetries of the crystal lattice and the way snowflakes grow as ice crystals combine together in the cloud to give the variety but keep the symmetry. Okay, let's move on to my favourite symmetric beast. I'm a cat fan. The tiger. Tigers are stripy, and the stripes are actually quite elaborate, and they are not perfect mathematical stripes. If you look at the ceiling of this building, you see perfect mathematical stripes in the beams on the roof. They're just absolutely like this. They're identical. Tiger isn't quite like that, but then a tiger is not just a nice flat mathematical plane. But if you look at the rear end of the animal, this bit, technically called the tail, you actually see very nice rings around the tail, fairly evenly spaced. They shrink a little bit towards the end, and then it's got the black tip. But that's the sort of most mathematical part of the tiger, I think, the tail. So, can we understand where those patterns are coming from? I want to convince you that it has a relation to symmetry. Now, tigers are not the only cats with patterns. There's a leopard, very nice leopard, doing typical leopard things, sits in a tree, dangles its legs down. A lot of the day it spends like that. Cheetah, runs around a lot. That is a jaguar, South American. And this is a clouded leopard. Such a beautiful pattern that it is an endangered species, much more endangered than most of them, just because some people think this is such a pretty pattern in the fur that they want basically to make something out of it and wear it. And of course, tigers are not the only stripy animals around. Very much not. Fish also. Some fish have stripes. Some fish have circular stripes. Some fish have spots. When we did the Christmas lectures in Japan in the summer, we couldn't get a tiger, so we got a cat. And this was a cat with a circular stripe on its side, a bit like this fish, but it wasn't blue. And a beautiful animal. Well, now our understanding of this mathematically, oh yeah, and you can have all sorts of interesting combinations of different spots and all sorts of things. Okay. This gentleman, whose centenary we celebrated last year, Alan Turing, now he is the person who founded the mathematical theory of animal markings. And it's kind of gone in and out of favour with biologists ever since. And every time they convince themselves, and the mathematicians, that it doesn't really work, or the latest incarnation doesn't really work, a few years later some other bunch of mathematicians or biologists, or fairly recently people in a dental school, come along and say, yes, it does. So there are places where it works, there are places where it doesn't. Take it too literally and it doesn't completely match the biology. Think of it slightly metaphorically as a type of model, and it works rather well. So Turing was actually interested in this animal, initially, the cow, which has these big blotches on the side. They are so iconic that you see them driving around on the side of lorries all over the world. We were walking past the local grocery store, and there's always one of these lorries parked outside, but last week it was a different company and it didn't have the black blotches on the white background. And we're actually quite disturbed by this. Suddenly the world had changed. Our 10-wheeler cow had disappeared. So, Alan Turing in his papers were discovered these plots. They're a little bit of a mystery, but they are clearly his mathematical model, which I'm going to talk about, of how these blotches on a cow or that kind of pattern forms, and we're getting some nice blotches. It's based on computer output, because if you look very closely at the little dots, they're actually numbers in, I believe, hexadecimal notation, which is what computers were using. He's clearly copied out all the numbers by hand and drawn contour lines through places where the numbers are all the same. The sort of way you get on a weather map, you have these lines where the pressure is all the same. Imagine doing that by hand on a grid which just has the numbers for the pressure. Well, this is what he's done. Instead of pressure, it's the concentration of some chemical. But he did also write and publish a research paper on this. And he was interested in stripes, spots, blotches on cows. He was also interested in the shape of creatures like the hydra, which is a little microscopic creature with a lot of tentacles. And he worked his way to a theory that what must happen, and this was kind of before modern genetics, and that's one of the reasons the biologists stopped being happy with it, because it was on a level where the influence of the genes was not explicit. But the idea was, think of the animal when it's still an embryo, fairly simple. The basis of the eventual pattern of markings is laid down chemically in the cells while it's still in an embryonic stage. You get what's called a pre-pattern. You can't see it, but if you could detect the relevant chemical, you will be able to. And he said, I'll call this chemical a morphogen. This is the typical kind of word scientists use for, I know what it does, but I don't know what it is. Morphogen, form generator. Yeah, or shape generator. Or in this case, marking generator. It's a thing that generates the pattern. And the idea is the pattern itself comes about as a result of two different processes. Chemicals reacting with each other, which changes the concentration of those chemicals, and diffusion, which spreads the chemicals slowly across the embryo. And so these are called reaction-diffusion equations. So you have complicated local chemical reactions, which are nonlinear in the jargon. They obey quite complex mathematical equations. And then global diffusion across the whole thing. And the diffusion kind of organises what the local nonlinear stuff is doing. And the result of this is you get patterns. And this was Turing's big insight. You get patterns. And these are experiments at the top and computer-generated pictures at the bottom of these reaction-diffusion equations, and we see spots and stripes and more complex-looking spots, and actually very complicated, rather irregular structures as well. And just to drive that point home, here's a fish called a boxfish with one of these rather... It's irregular, but the spacing between those yellow stripes is pretty much the same everywhere. There is a regular spacing to it, but the details are irregular. And a computed Turing pattern, which is qualitatively similar. I'm not suggesting these match in detail, but they're the same kind of thing. Okay. Now, Turing explicitly in his paper explains this in terms of what he called the breakdown of symmetry. This is my symmetry graph that I was talking about. And he says, basically, those are his words, but let me summarise. There's a problem. There's what looks like quite a difficult problem. The embryo, at the time the patterns are formed down before the animal grows, is essentially spherical. It's spherically symmetric. Superficially, at least, it's like a ball. If I rotate it, you can't really tell in which direction it's pointing. Okay, now biologically there are actually some markers for front, back, left, right and top, bottom already at that stage, but nonetheless, look at it, It just looks round. And it's obeying laws of physics and chemistry everywhere to produce the eventual animal. And if it was like a snowflake, which is six-fold symmetric and therefore does the same thing at all 6 corners, a sphere should do the same thing everywhere. It hasn't got corners. Every point on the sphere could be moved to any other point by a symmetry. So shouldn't it just grow the same pattern everywhere? In which case your horse that eventually emerges ought to be a sphere. But it can't result in a horse because a horse is not spherically symmetric. He has an answer to this objection, and okay, people wouldn't necessarily phrase this in terms of embryo turning into horse, but there is quite a period in the history of science where people didn't quite understand this point. And the idea was, if you have a symmetric system, its behaviour will be equally symmetric. And Turing says, no, this is not true, this doesn't happen. And it doesn't happen because the symmetric state can become unstable. Very tiny perturbations, little bumps on the sphere in the case of the horse, changes in the chemistry at one point or some region, can destroy the entire symmetry of the object because those small changes can grow. Instead of damping down and everything staying symmetric, they can grow, they can take over the structure, and the whole thing changes and it loses some of the symmetry that you thought was there. And he explains this. Turing obviously had a good sense of humour. I mean, this is in a journal paper. Example, if a rod is hanging from a point a little above its centre of gravity, so you've got something like a ruler which is pivoted just above the middle, and it swings, it will hang vertically downwards in stable equilibrium. Now when it does this, it's essentially symmetric from left to right, for example, it's hanging in the middle. Now he says, imagine a mouse climbing up the rod. If the mouse keeps climbing up the rod and goes past the middle and up towards the top, at some point the whole thing's top heavy. What does it do? It flips right over. And so this equilibrium becomes unstable. Instead of just hanging steadily, it flips over and it starts swinging from side to side. When it swings from side to side, in fact it's the time symmetry, it's in the same place at all times, that gets lost. It's not in the same place at all times, it's moving. But it's moving periodically, it's repeating the same motion over and over again, assuming there's no air resistance or friction. So after a certain period of time, it does the same thing. Does it again, does it again, does it again. Now if you actually draw a picture of the position of the pendulum with this mouse hanging on for dear life, swinging from side to side, and you draw it against time, you get some sort of curve which repeats the same structure over and over and over and over again. It's like stripes in time. Yeah? So we're seeing the pattern, but in this case we're seeing it in time. So if I only realised Turing had written this after I'd prepared my version of much the same thing. So instead of his rod, I have a rod as well, but it's pivoted at the bottom and held by a spring. And the spring is such that it likes to sit vertically, and if I move it to one side or the other, I stretch or compress the spring, and the forces that the spring exerts to push it back again are the same on both sides. So although I've only drawn the spring on one side, this whole thing as a system is left-right symmetric. And when it's vertically upright, it's in a left-right symmetric state. If I flip the whole thing over, the rod still appears to be in the same place. Okay? Now, I don't use a mouse. If I'd known Turing had written about a mouse, I might have put a mouse in, but it's more dramatic if you take an elephant him on top of the rod. And you don't have to be an engineer to look at this and say, that's not going to work. If that's a really heavy elephant, strong rod, but the spring is not going to be able to support the elephant, so it's going to do something like that. Well, now the whole thing has moved off to one side, and the state of that rod is no longer left-right symmetric. If I flip that picture, the rod goes over to the other side. Yeah? So although the mathematical equations, the whole system, has this left-right symmetry, the state that you observe does not. Why not? Because that vertical upright state, although mathematically possible, is not stable. Slightest breath of wind, and it will start to move, and then the weight of the elephant takes over, and down it goes until eventually you compress this amazingly powerful spring that will resist the downward force created by the elephant. So where's the symmetry gone? There's another solution that looks like that. Yeah? So you can have a symmetric system with a symmetric state, but if that loses stability, the system goes to an asymmetric state, but there are traces of the symmetry still remaining. There is a symmetrically related state that's still there. Now let's look at the same idea with a richer range of symmetries. Symmetries of the whole plane. Again, you can look around this room and see some examples. I talked about stripes in the roof. People online won't be able to see these stripes, but imagine a whole pile of stripes. Okay? So you have the symmetries of that sort of stripe pattern are, if you move it one stripe along, it still fits. Move it two stripes along, it still fits. But move the stripes into the gap between other stripes and you'll notice it's changed. So it has symmetries, but they're not slided to any position, they are moving very specific distances at right angles to its stripes, or slided along the stripes. You won't see any change. So symmetries of the plane are a much richer source of patterns, and there are basically four kinds, three major ones and another one I might as well mention. So take some shape in the plane. Here it happens to be a school teacher dragging a donkey for reasons that have nothing to do with this at all. It's a shape. And you can rotate that shape. You can reflect it in some mirror, not necessarily left and right, but it can be. Or you can also do a thing called a glide reflection, which pushes it along and flips it over. Okay. Now these are the basis of symmetries of patterns in the plane. So let's go back to Turing and the tiger and animal marking. Now it's not entirely the case that when the embryo grows, that's not exactly the right shape of domain. But there are a number of reasons in the way the patterns form that actually kind of unwrapping the animal into a blob with 4 bits sticking out and a tail end is not such a bad thing to do. And what he discovered was you can get interesting patterns forming, and you can also get these. There's one at the bottom that has one stripe, it's completely black. There's one just above it that has, well, half a stripe if you wish. One above it has a black at one end and white at the other end. A complete single unit of stripes. There's one that has black at 2 ends and white in the middle. And you can actually find sheep, for example, and goats, which have that sort of pattern. And then as you change the mathematical numbers, you get all sorts of different patterns. And he also looked at the, as I remarked, the rather symmetric bit that's on the back end of big cats. And he found you can get stripy patterns. It's a tapering cone. So you solve Turing's equations on a tapering cone. And you find stripes, and you find spots, and you find a wonderful set of patterns which are stripy at the thin end and spotty at the thick end. And in a sense, the mathematical reason is quite straightforward. If you've got stripes going round, they will be stable until there's enough room for them to do something different. And the main thing they can do that's different is the stripe breaks up into a series of equally spaced spots. So as the amount of room increases, you can get stripes breaking up by symmetry breaking into spots. So he proposed a theorem. Here is a computer calculation showing this kind of thing, but with a perfect cylinder. You get stripes, but it is possible for them to break up into a pattern of spots. It's actually an hexagonal pattern. That's very interesting about it. The successive stripes break in alternate places. One breaks like this, the next one is down here, then it's back like that, it's back like that. And if it's tapered, you can see similar things occurring. So Jim Murray has a theorem. Here's a theorem. A spotted animal can have a striped tail, but a striped animal cannot have a spotted tail. Okay? Proof, in order to get stripes breaking up into spots, you have to have a larger region of the domain. On the whole, the body of the cat is a lot bigger than the tail. And indeed, if you have stripes and spots mixed up at the rear end of the tail where it's nice and thin, you will see the stripes, and then they'll turn into spots. And to demonstrate this theorem, here we have a spotted cat with a spotted tail. And there we have a striped cat with a striped tail. And here we have a spotted cat with a striped tail, cheetah. And I don't have a picture to show you of a striped cat with a spotted tail. Okay? So, yep, so Jim is right. Okay, let me move on. So I want to tell you about sand dunes, where all of this in relation to symmetry is this is always easier to understand because we understand what a sand dune looks like. A pattern of chemical concentrations is something that we're not quite so familiar with. So what I want to show you is sand dunes actually have very similar patterns to animal markings. And the reason is they've got basically the same symmetries. They're patterns in the plane. One of the commonest patterns for sand dunes are called linear dunes. They're basically stripes. They're stripes across the desert. But instead of colours, it's whether the sand is high or low. They're formed by strong winds that blow in a constant direction. And these are in Algeria, photographed from a satellite. Here's another example of essentially the same kind of thing. That's whereabouts in Algeria you find it. This is the biggest set of linear sand dunes, or linear dunes, they're not sand, in the solar system. And it's on Titan. It's photographed from the Cassini satellite. And there's just this vast set of linear dunes on Titan. So these things don't just occur on the Earth. Now there's also these wonderful crescent-shaped or bucket dunes. These are in Egypt. Those are on Mars. Here's a more complex field of these dunes. And it's in the Namib Desert. And the way they form is you essentially get a pile of sand builds up as the wind blows. And the wind blows over the top, and it forms a big vortex that sweeps out the bit in the middle of the crescent. The region if you've got a crescent, the region in the middle is where this vortex is sweeping stuff out and funneling it out to the edges. So the wind actually blows from if the crescent is shaped this way, the wind's blowing that way. So the arms of the crescent are kind of being pushed along. And in fact, the entire dune moves. So as the wind blows over the top, this is the standard way all sand dune patterns form. sand gets moved around, the shape of the dune affects what happens, and it also affects how the wind blows. It affects the aerodynamics. So there's this interaction between the wind and the sand. And even if it's a steady wind, once the sands change shape from flat, the effects of the wind are different in different places. So sand erodes from the windward face, gets pushed over the top, dumped on the other side, the lee side, and the sand moves, the dune moves. And people who study this kind of thing, they classify dunes into 6 main patterns. There are others, but these are the main ones. So there's the Bacchanal crescent dunes, linear, longitudinal. Basically, they point in the same direction as the average wind speed. Transverse dunes, which are like stripes as well, but they are at right angles to the wind speed. Parabolic dunes, which form usually at the edge of where the desert meets water. And they're kind of pinned in place by the vegetation. Baccanoid dunes, which are wobbly, and star dunes, which are dotted all over rather randomly. So we can model this mathematically by saying, well, we'll take a model desert with flat sand, wind blows at constant speed, fixed direction, and the desert is infinite. The symmetries are all rigid motions, but we've got a wind. So it's rigid motions that preserve that wind direction. So I can slide the desert but not rotate it. I can reflect it, but only in a mirror in the points the same way as the wind. And then I can look at the group of symmetries and say, if symmetries break, then that means some of the symmetries no longer apply to the state of the desert, but some smaller set of them may. Remember I was talking about the mouse on the pendulum, saying if you draw a picture, if that pendulum was always in the same place, the picture of where it was would just be a horizontal straight line, and you could move it to any position, through any distance, any time, and it would look exactly the same. But if it's oscillating periodically, I can move it by 1 period, 2 periods, 3 periods, -1 period, go the other way. So a continuous set of symmetries in some direction, when it breaks, what it tends to do is it breaks up into discrete translations in that direction through some multiples of some fixed distance or time. And this is what we see in the dunes. Think about transverse dunes. The wind is blowing vertically. The symmetries could slide those dunes up and down to any position you like. They could slide the desert sideways to any position, and they can flip it that far. What symmetries does this pattern of dunes have? Any translation at right angles, any distance whatsoever, fixed distances along the wind direction. So the symmetry along the direction of the wind has broken. And you can predict this pattern of stripes just from the symmetries. You need to know when that pattern is stable, but you can predict that's a possible pattern. Now with the Baccanoid dunes, where it's like that except they become wavy, we've broken another set of symmetries. The left-right translations, they're not through any distance anymore. They are through specific multiples of the wavelength as well. So a second group of symmetries has broken to get the Baccanoid dunes. And in fact, if you imagine taking the sharp pointy bits and just pinching them off, you get a pattern of spots, which would again have specific translations in both directions. Yeah. Linear dunes are very similar to the transverse ones in terms of the symmetry, except it's now the translations of right angles to the wind that have broken. To give stripes, the ones in the wind direction remain. Bacchanal dunes, you can imagine some kind of lattice of copies. This is a very, very idealised picture, or you might imagine that they're perhaps staggered with respect to each other. So there's one, then one, then one, then one, like that. So again, their symmetries in both directions have broken. Parabolic dunes, they've lost the symmetry of translation altogether in one direction. There's nothing there, you can't move them. But you can still move them specific amounts left and right. And finally, the star dunes, which probably are best thought of as not really having much symmetry at all. Everything's broken. They do have sort of local, vaguely rotational symmetries. Star dunes form when the wind on average doesn't go in any particular direction. One day it's coming from the north, another day it's coming from the east, another day from the south, southwest, whatever. No prevailing direction. So the pattern has no prevailing direction either. So now we see that the same symmetry principles are applying in two different mathematical systems, or two different physical systems. The markings on animals, where it's a chemical pattern, which we now know is related to the genetics, but that's another story, and the pattern of sand dunes, where it's a pattern of sand. And roughly speaking, any physical system in the plane that starts out being symmetric under lots and lots of rigid motions in the plane, you'll get the same kind of range of symmetry types of patterns. So the same mathematics will apply to lots of different systems. And that's what makes this very powerful. Okay, I'd like to end up with something I'm pretty sure I talked about at Gresham College about 18 years ago, possibly using the same slides to some extent, which is the animal movement. Okay, here is a lovely sow trotting along. Yep. What's mathematical about that? I was actually giving a lecture to some school children in Malta, and this is the point at which they woke up. Once we got the trotting pig, then I had their attention. So I probably should have put, well, I did put the pig quite early, but then we forgot about it. Anyway, so you probably know the poem, yes? The centipede was happy quite until a toad in fun inquired, which leg goes after which? This raised its mind to such a pitch, it lay distracted in a ditch, considering how to run. I'm not going to talk about centipedes, they are a little bit too complicated, although the mathematics I'm going to tell you about does seem to apply to them with a few interesting predictions. But the main point here is that animals move in lots of different ways. Now we've got a rabbit. The rabbit was a hare, actually. The hare is bounding. The horse there is trotting. The elephant is walking. And I can be pretty certain about that because essentially there's only one pattern that elephants move with. That's not quite right, but it's close. And the insect has 6 legs. And that one, I think, is doing what they call a tripod gait, which is essentially that the legs move in groups of 3. But one at the front, one at the back, and the opposite one in the middle. If it's not doing that, it's doing a thing where essentially it's like a walk. It's this leg, that leg, this leg, that leg, this leg, that leg. Oh, wow. Okay, metachronal gait, that's called. And I'm not quite sure what the bull is doing. The cheetah is doing what's called a transverse, no, it's called a rotary gallop for the cheetah. It's getting so, it's going so fast that actually the back legs have got in front of the front legs, you can see. It's catching up with itself. And the millipede, which is an even bigger challenge than the centipede. Okay. These things are called gaits. And it's actually useful. There are lots of applications of this kind of, it's a mixture of mathematics and physiology, basically. So there are medical reasons for wanting to understand human gaits, because people have problems wrong with their knees and hips, and, tell me about it. And it's good for sports science. Mo Farah didn't just win his medals by being very good at running. There's a lot of analysis and training is aimed at specific things that sports scientists have understood about how to run fast. Or you can use it to analyse dinosaur tracks and understand how the dinosaurs move. Or you can use it to look at human evolution. Nice picture from Nature not too long ago, suggesting that running was a major factor in the way the human body has evolved. Or you can look at robots with legs. How can you make them work? Very useful to the US military who want to defuse bombs on firing ranges and things like that. Or you can use them to explore planets. I mean, we just landed another wheeled robot on Mars, but that's because the engineers really understand wheels. Legs will be the coming thing, but not quite yet, because the wheel is a little more reliable, but they've gone to some lengths with the latest Mars rover to make sure that its wheels don't get stuck and so forth. Okay, and future applications send out robots all over the solar system, if not beyond, and they may not have wheels and they may not have legs either. They may have all sorts of structures. Okay, so the subject of gate analysis was started by this chap, born Edward Muggeridge. Rapidly became Edward Muybridge. Sounded posher. And he took photographs of animals moving. And let me run you through one or two of these. So when the elephant walks, and indeed when any other four-legged animal walks, the pattern is this. Look at when the left rear leg hits the ground. It will be followed by the left front, then the right rear, then the right front. If you look closely at that picture, this is what you see. That foot, that foot, that foot, that foot. If you ever see them, and I have sometimes seen animations on television, they've got better now. But in the early days of animations of dinosaurs and things, sometimes it was that foot, that foot, that foot, that foot. Back leg, front leg, front leg. No, they don't do that. Back, front, back, front. That's how it works. Our pig, like the horse, is trotting, and you can recognise a trot because the legs are locked together in pairs. A diagonal pair hits the ground, and then the other diagonal pair hits the ground. Those two, then those two. Okay? And all of these have patterns. If we go to the canter, now that's rather complicated. Left rear, then a diagonal pair together, and then the missing leg hits the ground after that. And that's why you get this rather odd-looking structure in the legs. Transverse gallop, an elk here is doing it. Left rear and then right rear with a slight delay. Then left front and right front with a slight delay. Those two, then those two. Clippity, cloppity. Right. The camel, racking or pacing. I still don't believe this. Both legs on the same side move together. Then the other two do. What I really don't believe about it, I can just about believe with the camel, giraffes do it. Because it's an enormously tall animal, it picks up both legs on the same side. we were in Botswana a few months ago. No, they don't move. They can move fast, but they can also move quite slowly, and they do it the same way. It is quite a puzzle. So mathematically, we represent these as a pattern of what are called the phases of each leg moves periodically. The phase is the timing of when it hits the ground. So for the walk, you have this pattern: hit the ground at time 0, quarter of a period later, the front leg on that side, half a period later, then 3/4 of the period, the legs the other side. Yes, you can see what these pictures show. And you can look at all of the different gaits in terms of these patterns of phases. So for the trot, it's 0 on one pair, half on the other pair. For the pace, 0 on one side, half on the other side. For the bound, the hare, which I haven't shown you pictures of, back, then front. Yeah? Think of a dog moving really, really fast. Then it gets more complicated for things like the transverse gallop, the rotary gallop, which is what a cheetah uses, which is very similar, but one end is switched, left, right, compared to the others. The canter, which is really quite bizarre, but has this one diagonal pair is going out of phase 0 to half, 0 to half. And the other pair are hitting the ground together, which are the two basic two-legged gaits. Human beings do this. When we walk, it's left, right, left, right, left, right. When it's children hopping along, it's both feet together. If you try and do that when you get older, it doesn't work. A horse cantering does both at the same time. And then there's the pronk. North, 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 north. That's a pronk. Whole animal, straight up. Okay? So here's the pronk. So we have at least 8, there are actually more, patterns, and 5 of these are very symmetric. The 4 along the top, and the pronk is the most symmetric of all. In fact, the most symmetric, even more symmetric than the pronk, is simply stand there, do nothing. All the legs are doing the same thing, and they're doing it at all possible times. Time symmetry has not broken. If the animal wants to move around, it breaks that symmetry, and the simplest thing is to move periodically. And if it's not got anything else to do, it kind of wanders around in a fairly rhythmic movement. So, what is it that's creating these patterns? This is kind of reverse engineering the physiology from the behaviour. And to cut a long story short, they're produced by something called a central pattern generator. This is a network of nerve cells that creates the basic rhythms. There's a whole pile of other stuff goes on to control whether you stop and have a look round, or whether you see the lion coming and run away at high speed, whatever. But the default rhythms come from a network of nerve cells somewhere in the spine. It sends signals to the muscles in the legs. It's not in the brain, it's not in the legs, it's somewhere in between. And you can deduce what it probably looks like. It's actually very hard to dissect out. By studying the mathematics of coupled oscillator systems. So let's take the simplest one. If I have 2 mathematical units coupled together, there are 2 common patterns that you will see. They both do the same thing at the same time, or they take turns. And I'm showing here with 2 pendulums. You've got pendulums that are swinging like this, or pendulums doing that. It is possible to do other things, but it's much rarer. And this is to do with the symmetries interacting with the phase shifts on the different oscillators. And you can do the same thing with 4 oscillators in a ring, and then you find patterns like all 4 of them do the same thing, or they alternate, left, right, in terms of 0 to half, 0 to half, and so on. You get different patterns. So if I draw pictures of the phases, in fact, these are the 4 patterns you expect in this ring. All 0, 0 and a half, alternating, a quarter shift as you go anti-clockwise, a quarter shift as you go clockwise. And these are a bit like, that's like, the first one's like a pronk, the second one is a bit like a pace, or a trot particularly. These 2 look like a walk, and one of them is walking backwards and one of them is walking forwards. Now, if you try and match that up to the animal, it doesn't actually quite work. And what about the others? What we think is going on, at least in the simplest possible network that can do this, is you don't use 4 oscillators, you use 8. And you use 2 for each leg. And physiologically, we think one of them is essentially pulls the leg forwards and the other one pushes it back again. They control muscle groups that have that effect. Because muscles pull, they don't push. Yeah? But you can think of the patterns by just looking at the bottom 4. These are perhaps the muscles that push the leg. And then above them are the ones that pull. And so if you write down all the patterns that are possible in this kind of network, for example, you can get a pattern where the phases go 0, 1/4, half, 3/4 up the left-hand side and then feed back and keep doing it. But on the other side, it's delayed by half the period. This is one of the patterns. There are 8 patterns for this network, basically. Well, if you just look at the bottom 4, that's the walk. That is exactly the walk. Whereas if we have this pattern, which can also occur, and just look at the bottom 4, you recognise the trot. That's the bound. 0, half, 0, half. That's the pace. And that's the prop. And you'd expect to do it with 4, but there are some subtle mathematical reasons why that doesn't seem to be correct. And then these things can occur as well, but it's a more complicated story. Now, when we did the maths, we realised that there is one pattern we hadn't noticed anywhere, which looks like this. 0, 1/4, half, 3/4, like a walk, but the same on both sides. Now, it's not the bound. The bound is back, front, at equal intervals of time. 0, half, 0 to half. This is 0, 1/4, what's happened, 0, 1/4, something, didn't know. Then we went to the rodeo. And we saw the bucking broncos. And then, of course, we realised that good old Mybridge had seen all this before. The back legs hit the ground, then the front, then actually the whole animal hangs in the air for quite a long time. Look at that picture. From top to the second row, it's done one, and it's still not come down completely. And when we looked at the video of the thing we saw in the rodeo, it is almost exactly 0, 1/4, the legs, and then the animal sort of getting itself back on the ground again. So it's not 100% confirmation of the theory, but it is at least consistent. And I'll stop there. Thank you very much. I overran slightly.